Let us try to solve some basic problems related to series and parallel combination of capacitance. So the first problem is you have to calculate the value of the unknown capacitance C if it is given that CAB, that is the equivalent capacitance between A and B, is 1. This is what the problem has provided. CAB is 1 and you have to find C. So let us try to resolve this on the basis of series and parallel combination. So it is quite obvious that C1 and C2 are in series. So for the combination of C1 and C2, if they are in series, their equivalent capacitance will be 8 into 4 by 8 plus 4. That is 32 by 12. That is 8 by 3 microfarad. So you can replace C1 and C2 by 8 by 3 microfarad. Next, C4 and C5 are in parallel. So their equivalent capacitance will be the sum of these two. That is 4 plus 4, that is 8 microfarad. Now C4 and C5 will be replaced by 8 microfarad. So if we replace C4 and C5 by 8 microfarad, that 8 microfarad will be in series with 1 microfarad. So for 8 microfarad and 1 microfarad in series, we again get 8 into 1 by 8 plus 1, that is 8 by 9 microfarad. So now you see this C4 and C5 replaced by 8. Series combination of 8 and 1 will produce 8 by 9, and now that 8 by 9 will be in parallel with the combination of C1 and C2, that is 8 by 3. So this circuit diagram will be simplified as this is C, this is 8 by 3 microfarad, and this is 8 by 9 microfarad. Now because they are in parallel, they will simply be added. So 8 by 3 and 8 by 9. So the parallel combination of 8 by 3 and 8 by 9 will produce 72 plus 24, that is 96 by 27 microfarad. So now 8 by 3 and 8 by 9 will be replaced by 96 by 27 microfarad, and that will be in series with C. So this equivalent network will become something like this. C, this point is B, this point is A, and this is obviously 96 by 27 microfarad. Now it is given that the equivalent capacitance between A and B is 1 microfarad. So they are in series. So therefore we can now write 96 by 27 into 1 divided by 1 plus 96 by 27, that is equal to CA. This is C plus, so this is 96 by 27 into C divided by C plus 96 by 27, that will produce the equivalent value, that is 1. So which means this will simplify like 96 by 27 C is equal to 1 into C is C plus 96 by 27. So if you take C to the left hand side and take common, we will get C into 96 by 27 minus 1, that is 96 by 27. So 96 minus 27 will give you 96 minus 27, that is 9. Sixty-nine C will become 96. That means this 27 will cancel out. So which means that C will be 96 by 69 on cancelling with 3, this is 32 divided by this much microfarad. So the value of C will be 32 by 23 microfarad. You can note it down. Take a pause and note it down. Now let us move to the second problem. You have to find the equivalent capacitance between A and B when it is given that C1 is 1 microfarad, C2 is 2 microfarad and C3 is 3 microfarad. Now in these type of problems, it becomes difficult to analyze which capacitors are in series or which capacitors are in parallel. In those situations, what we do is we assume that there is a battery connected between the terminals A and B. The battery is an ideal battery of any potential difference you can assume, 10 volt, 20 volt, 5 volt, whatever it is. So just for the sake of this problem, let me assume that between A and B there is a ideal battery of V volt. The potential difference between the terminals of the battery is V volt, or you can say the EMF is V volt. So if this is V volt, the positive terminal can be expressed as plus V and the negative terminal can be written as 0. That is V minus 0 is V, that is V volt battery. So which means that this point A is again at V volt and this point B is at 0 volt. If I move along this direction, I do not encounter with any circuit element because this is just a wire. We assume that wires have no resistance at all or no capacitors at all. That means if there is no capacitor or no resistor or no inductor or any electrical component along the connecting path, its potential difference is unaltered. So if this is 0 volt, this is also 0 volt. There is no electrical component along this path, so this point is also 0 volt. And similarly, if this is V volt, this point is also at V volt. Along this path there is no electrical component, so this point is also at V volt. So now you see that this plate of C1 and this plate of C1 are at the same potential 0 volt, which is also same as that of this plate of C3. So C1, C2 and C3, a plate of each of these capacitor is at 0 volt, and this plate of C1, this plate of C2 and this plate of C3 is at V volt. So 3 plates of each of the capacitors are at V volt and the other 3 plates are at 0 volt. That means these 3 are in parallel. So this can be simplified as so this is V volt, this is 0 volt, so this is C1, C2 and this is C3. So 3 plates are at V volt and 3 plates are at 0 volt. That means they are at parallel. So the equivalent capacitance CAB will be the sum of these 3, and C1 is 1, C2 is 2 and C3 is 3, so the value is 6 microfarad. So the equivalent capacitance between A and B is 6 microfarad. You can note it down again. Another problem. You have to again find the equivalent capacitance between A and B, and C1, C2, C3 and C4 are of these values. C1, C4 is 1 microfarad and C2, C3 is 2 microfarad each. You have to find the equivalent capacitance between A and B. Again, this might be difficult to resolve into series and parallel. So let me again assume that there is a battery of EMF V volt connected between A and B. So if this is V volt, then this is plus V and this is 0 volt. So this is V, this means this point is at V, this point is at V, this point, that means this point and this point is also at V, because there is no electrical component along this line. So if this point is at V volt, this point is also at V volt. Similarly, if this is 0 volt, point B is at 0 volt, which means there is no electrical component here, so this point is also at 0 volt. Now again you realize that this plate of C1 is at V volt, this plate of C3 is at V volt, and this plate of C4 is at V volt. This plate of C1, this plate of C2, and this plate of C4 all are at 0 volt. So what we have is C1, C3 and C4 a plate each of C1, C3 and C4 are at V volt, and that is the point A, which is at plus V volt. Now this is C1, this is C3 and this is C4. Now again you see that C3 and C2 are in series, so these two are in series, and now a plate each of C1, C2 and C4 are at 0 volt. So now you can say that this point is B, which is at 0 volt. So the circuit has been simplified in this manner. Now it becomes very easy. C2 and C3 are in series. So for the combination of C2 and C3, it will be C2 C3 by, because they are in series, C2 plus C3. So C2 is 2 and C3 is also 2. So 2 into 2 by 2 plus 2, that is 4 upon 4, that is 1 microfarad. So C2 and C3 will be replaced by a 1 microfarad capacitor. And now C1, 1 microfarad and C4 are in parallel. So the equivalent capacitance between A and B will be C1 plus 1 plus C4. C1 is and C4 both are 1. So 1 plus 1, that is 3 microfarad. You can note it down. Now let us take another type of circuit which is called as Wheatstonebridge. Another type of circuit which is called as Wheatstonebridge. Now this Wheatstonebridge is a network of capacitors or resistances. For the time being we will talk about capacitors only. So this network is of this form, suppose. Suppose between each terminal there is a capacitor. Suppose this point is point A, this point is point B, this point is suppose M, this point is suppose N, this is C1, this is C2, this is C3 and C4. In a network of capacitances, it is quite possible that in some situations the ratio of C1, C2 and C3, C4 is such that the fifth capacitor C5 is meaningless. That means the potential difference of the points M and N becomes same due to a particular value of C1, C3 and C2, C4. So that situation will give rise to a balanced Wheatstonebridge. So the Wheatstonebridge is balanced if and only if the ratio of these C1 by C2 is equal to C3 by C4, or you can say that C1 by C3 is C2 by C4. Then M and N are at same potential, and in that situation this C5 can easily omitted, because no charge will be deposited on its plates because M and N are same potential. So no charge is flowing along this segment. So the presence of C5 is totally meaningless, and this equivalent form of this network will just become so C1, C2, C3, C2 and C4. Between the points A and B, it becomes very easy. C1 and C3 are in series, C2 and C4 are in series, and the combination is now in parallel. So it becomes very easy to analyze if we can realize the structure of this form, provided it is a balanced Wheatstonebridge and the ratio of the capacitances are such that C1 by C2 is C3 by C4. Then only we can eliminate this C5. Let us take some examples of Wheatstonebridge. The next problem is this type. We have to again find the equivalent capacitance between A and B, and this is the network of capacitors. Now in this problem, at the end step somewhere, we will come across the Wheatstonebridge. It looks a bit complex, but it can be simplified, and ultimately it will become a balanced Wheatstonebridge. So let us try to solve this problem. So again, because it is difficult here to resolve which capacitor is in series and which capacitor is in parallel, so let me assume that there is an ideal battery connected between A and B. A battery of V volt is connected between A and B. The positive terminal of this battery is connected to A and the negative terminal is connected to B. So V volt means the potential difference is V. So this can be taken as plus V volt, and this is obviously 0 volt. So now you see that if you follow this line, there is no electrical component. So up to this plate, the potential difference remains 0. Up to this plate, the potential difference remains 0, and up to this plate, the potential difference remains 0. Similar to this one, plus V. There is no electrical component, there is no electrical component, there is no electrical component. So these three plates are all at positive potential V. Now we cannot say what are the potential of these points, because along this direction we have come across a capacitor, so it is never 0 volt here. Neither along this direction you can say that there is V volt, because from V there is a there is a capacitor on which some charge will deposit and the potential difference will get modified. So this point is never at V, neither this point is at 0. So let this be of some different value. Let me assume that this point is at X volt. If this is at X volt, then this plate are also at X volt. There is no electrical component along this line, so this is also at X volt, and these two plates are also at X volt. Similarly, let me assume that this is at Y volt. So if this is at Y volt, this plate, and this plate all are at Y volts, because there is no electrical component along this direction. So this is also Y volt. Now we try to simplify this network on the basis of the potentials. So you have point A, which is at V volt. There is some point which is at X volt. There is some point which is at Y volt, and there is the point B which is at 0 volt. You see that between A and X, between V volt and X volt, you have a capacitor, another capacitor, two capacitors 15 and 10 are between V volt and X volt. So now we can express it in this form. A 15 microfarad and a 10 microfarad are between V volt and X volt. Between X and Y, there is nothing else than this 13 microfarad. Between Y and B, between Y and B, that is between Y and 0 volt, there is 1 microfarad, there is 1 microfarad. So this is 1 microfarad and this is 1 microfarad. Now between A and Y, between A and Y or V volt and Y, there is this 10 microfarad. Between X and B, between X and 0 volt, between X and 0 volt, between X and 0 volt, there is this 5 microfarad. So this is 5 microfarad. So this is the simplification of the above diagram. Now you will see that 15 and 10 are obviously in parallel, 1 and 1 are in parallel. So 15 and 10 will produce 15 plus 10, that is 25. So this network will now simplify as 25 microfarad between V volt and X volt, that is point A. Between Y and 0 volt or point B, 1 and 1, these are in parallel, so they will be added up, will produce 2 microfarad. And between A and Y, it remains, sorry, I missed the point, X and Y. So between X and Y, this 13 microfarad was already there. Between X and Y. So between X and Y, there is 13 microfarad. Between A and Y, there is 10 microfarad. And between X and B, that is 5 microfarad. Now, if we look at this diagram carefully, this is a balanced Wheatstonebridge, because 25 by 5 is same as 10 upon 2. 25 by 5 is 5 and 10 by 2 is 5. So this behaves like a balanced Wheatstonebridge. So if you simplify this diagram, taking point X and Y, and A and B, B was at 0 volt, A was assumed to be at V volt, this point was at X volt and Y volt respectively. So between A and X, now there is 25 microfarad between A and X. Between A and Y, there is 10 microfarad. Between X and B, there is 5 microfarad. And between Y and B, there is 2 microfarad. And between X and Y, there is 13 microfarad. Now this 13 microfarad will become meaningless, because the point X and Y are at the same potential. As you see that 25 by 10 is 5 by 2. 25 by 10 is definitely 5 by 2. 25 by 10 is 2.5, 5 by 2 is also 2.5. So from this you can say that point X and Y are the same potential, and so no charge will deposit on this 13 microfarad. This can be eliminated. So this circuit will again simplify as this is X. Now this point is also X, because X and Y are the same potential. So whether you write X or Y, there is no connection between them. This point is B, this point is A. This is 25, this is 10, this is 5, and this is 13. So now 25 and 5 are in series, 10 and 2 are in series, and the combination is again in parallel. So just take a pause and note it down. Okay. So now this is the last simplified diagram. So 25 and 5 are in series. So 25 into 5 by 25 plus 5, that is 25 into 5 by 30, that is 25 by 6 microfarad. And 10 and 2 are again in series, so the combination will be 10 into 2 by 10 plus 2, 20 by 12. So this is 5 by 3. Now 25 by 6 and 5 by 3 are in parallel. So the last simplification will be between A and B. We have 25 and 5. They have produced 25 by 6 microfarad, and 10 and 2 have produced 5 by 3 microfarad. So between the points A and B, this is the last simplified diagram. So it is obvious that both are in parallel, so the equivalent capacitance will just be the sum of them. So now CAB, or the equivalent capacitance, is 25 by 6 plus 5 by 3, which is obviously 25 plus 10 by 6, that is 35 by 6 microfarad. You can note it down. Now let us take another problem. So suppose a network is given in this form. Now it is given that this extends up to infinity. This extends up to infinity. This set is a repetitive set. This set is repetitive nature, and it is repeating up to infinity. So you have to find the equivalent capacitance between A and B. Equivalent between A and B, provided all are at same values C, and it is given that C is 2 microfarad. So you have to calculate the equivalent capacitance between the points A and B of this repetitive network, where each C is equal to 2 microfarad. So now what we do is, because this set is repeating itself, so equivalent capacitance, whatever the value between A and B, suppose the equivalent capacitance is X microfarad. Then actually, if you replace, or if you just omit one segment, the value of the capacitance does not alter, because the network is repeating up to infinity. So out of a very large value or a very large number, if you just omit or delete a particular segment, then you get the same result. So if this is not present, this value is also X. If this one is not present, the entire value is also X. If this one is not present, the entire value is also X. So this can be expressed as X. C, and this is point B, this is point A. So this X can be replaced by this repetitive network. And also we have assumed that the equivalent capacitance between A and B is X. So now you see that C and X are in parallel. So this can be simplified as C plus, this is C plus X, this is C. And now C and C plus X are in series, and the equivalent capacitance is X, that we have already assumed. So now you can say that X is C into C plus X by C plus X, which means 2C plus X square equal to c square plus cx. That means x square plus 2cx minus cx is plus cx minus c square is equal to 0. So this is a quadratic equation. Note it down. If you solve and find the value of x, you will get the equivalent capacitance between A and B. Remember, we have just assumed that one segment of this repetitive network can be omitted so that the remaining value or the remaining segment has a capacitance which remains unaltered. On that basis, this segment is of value x, that is the equivalent capacitance x. So if you can solve this, we will get the equivalent capacitance x. It was already mentioned that C is 2 microfarad. So what I have is x square plus 2x minus C is 2. So that is 4 equal to 0, which means x equal to minus b plus minus b square minus 4ac, that is by 2a. So this value cannot be negative, so the negative is meaningless here. So this becomes minus 2 plus root 20. Root 20 is 5 into 4, that is 2 root 5 by 2. So you get the value root 5 minus 1. So x is root 5 minus 1. X is root 5 minus 1. This is the equivalent capacitance of the network. Hence, CAB is root 5 minus 1 microfarad. Hence, the equivalent capacitance between CAB is root 5 minus 1 times root 5 minus 1 microfarad, which is approximately 1.236 microfarad. 1.236 microfarad.